we're there. And the answer is that, yeah, you should be fine because I didn't have quantum either. I'm just teaching myself this stuff as we go. All right. So we were talking last time about how to formulate our guess for the wave function in the Schrodinger equation. And we're going to do this by starting with an alphabet of atomic orbitals. Laser, okay. Atomic orbitals, this phi sub k. K is each atom in the molecule. And we're going to have an alphabet of atomic orbitals for each of those atoms. And they're going to be weighted by these coefficients C. And they can all potentially contribute to a particular molecular orbital. So, for example, if our molecule were methyl, our atomic orbitals would include a 1s orbital for each hydrogen, and then methane rather, 1s orbital for each hydrogen, and then a 2s, 2p, x, y, and z orbitals for the carbon. And we would mix all of those together, 8 orbitals in to get 8 molecular orbitals out. And each one would have a component from orbitals on each atom in our structure. So, but we're going to keep it simple. We're going to say, what if we have just 2 atoms coming together? And let's actually make it even simpler than that. Let's focus bringing let's have them be hydrogen atoms. There's only a 1s orbital available. So we're going to mix 2 atomic orbitals, phi A and phi B, and they're weighted by these coefficients. And then we started with the Schrodinger equation. We want to evaluate, we want to know what the energy is, we want to know what the wave function looks like, we want to know what these coefficients are. And it looks like we've got way too many unknowns, but it looks like, the math is going to work out just fine based on some assumptions that we're going to make. So what we've done to the Schrodinger equation is we've multiplied both sides by the complex conjugate of the wave function, and then we've integrated that over all space. Because energy is a constant, it can come out of the integral. And so we have the Hamiltonian operator applied to the wave function times the complex conjugate of the wave function divided by this integral on the bottom, which is just something that's called the square modulus or the probability density. This is a wave function wave function complex conjugate times the wave function integrated over all space. Okay, so we're just going to substitute in this linear combination of atomic orbitals into the integral, and this is where we started last time. Oh, sorry, we got to get rid of that hovering record sign on the screen, sorry. Okay, so we've simply replaced the wave function with the atomic orbital description. And what we're going to do now, actually, go ahead, Dakota, thanks.
The denominator there, the square modulus of the wave function over all space.
Uh-huh.
Is it true that has to be 1?
It has to equal 1, and we're going to make it that way by normalizing the coefficients at the very end.
Okay, so even though it's just dividing by 1, we need it there?
Yes, we need it there now because we don't know what the coefficients are. And so we're going to simplify this expression into something that's going to allow us to get the coefficients. But yeah, we need it there. We can't just say that it's 1 at this point. Afterwards, when we finally want to get numerical values for the coefficient, that's going to be the constraint we're going to put on it that's going to allow us to get real numbers out.
Okay, yeah.
All right, so one of the rules of integration is that you can, if you take the integral of a sum, you can actually separate that out into the sum of integrals. So as we were talking last time, we're going to take the first term in our wave function here, we're going to apply the Hamiltonian to it, and then we'll do the same thing for the second term in our wave function. So we'll have Hamiltonian applied here, Hamiltonian applied there, and then we'll just do the distributive property where we multiply this term by Hamiltonian of that, this term by Hamiltonian of that, and so on. I don't want to write out the algebra because it's just essentially doing the same math as it would take to do a plus b squared. You're going to use the FOIL method. Curses, foiled again. But if you expand it all out, this is what you get. And we've brought the coefficients out front because they're constants. So let's just remind ourselves where this first term comes from. Hamiltonian applied to CA phi A, then multiplied by CA phi A. The integral stays here. Both CA constants come out front, and you get CA squared. All right? And then each of the rest of these terms, CA, CB times the Hamiltonian integral of Hamiltonian of phi B multiplied by phi A, CA, CB, this time phi B is in front and phi A is here, and then a CB squared term. Sort of see where that's coming from, okay? On the bottom, we're doing the same, only there isn't a Hamiltonian, so this is just distributive property. All right, so now we're going to make things easier because we're going to, and I'm actually not just going to, I think maybe I'll write some of this down instead of, so that we can go through it. Sometimes it's better to write than to point to stuff and say it. So we're going to simplify this by replacing these integrals with some symbol that will represent the integral but be less tricky to write. So we're going to define this term, the Hamiltonian applied to wave function A, multiplied by wave function A, and then integrated over all space. We're going to call, I'm getting confused there. We're going to call that H sub double A, and we're going to call this the core integral. And this represents the kinetic energy plus the potential energy of an electron in the starting atomic orbital A. Okay, so that's what it would be. Go ahead, Austin, thanks.
Yeah, so looking at the top and with the E equals
Sure.
integral of the sum.
Yeah.
So do you have to divide by anything to get energy, or is it energy just on its own?
Let's see. As we've written it here, that's just energy on its own.
So you don't have to divide it by the wave function squared?
No, what we have done is we've multiplied both sides of the Schrodinger equation by the complex conjugate of the wave function, and we've integrated it over all space. Then we've reminded ourselves that the energy is a constant. So we take it out of there, and then we divide by this basically wave function squared on the bottom. Is that?
I think so. So dividing by the wave function squared gives you the probability, or that's what gets you to it?
Well, it's that is a good question. Ideally, if you knew what the wave function is, you could simply apply the Hamiltonian to the wave function, and that would spit out the wave function multiplied by the energy. Okay? We know what the Hamiltonian is, but our problem is we don't know what the wave function is. So we're trying to figure that out, and because we don't yet know what it is, we can't just apply the Hamiltonian to it. What we have to do is a little bit of math. Basically, we want an expression for the energy, because in a little bit, we're going to say, how can we find the coefficient that gives us the smallest energy possible? And it turns out that's just going to be a little bit of calculus. Okay, other questions? Yeah.
Also, using a larger basis set, will that give us a lower energy? Offers more flexibility.
Yeah, it's a good question. If we use a larger basis set, are we going to have greater flexibility? And the answer is, in many cases, yeah.
In this case, our basis set size is 2.
That's right, because we're keeping it simple. And it's only because I can't do the math if we do more than that. So, sorry. We'll have programs that can do that math. But there's some concepts here that are transferable across all molecules and I want you to see the mathematical basis for it. Others? Okay. So the core integral is basically it's basically just the energy of an electron in that atomic orbital, sort of where you start at. Okay. The same thing is true for the following integral based on the B atomic orbital, which we're going to call HBB. This is the same thing. It is a core integral, except it's for atomic orbital B. And for our case today, we're going to say that A and B have the same energy. So we're going to let HA equal AA equal H double B, which would be the case if you had two hydrogen atoms coming together, right? When they're apart, they're exactly the same. So the core integral of an electron on this hydrogen atom has got to be exactly the same as the core integral of an electron on that hydrogen atom. Okay, with me so far? Now, what about that weird one where you have the Hamiltonian applied to wave function B multiplied by wave function A? We're going to call that, unsurprisingly, HAB. And this has a physical meaning too. This is called the resonance integral. What it means is this is the stabilization you get by allowing the electron to be shared between nuclei A and B. And this is due to lower, and we'll learn this again in a little bit, but this is due mostly to the lower kinetic energy of an electron that's spread out between the two nuclei instead of being near one nucleus. I actually read that, and I taught in 351 that one of the reasons that bonding works is that you get lower potential energy because you're in between two nuclei, and there is a favorable Coulombic term for attraction of the nucleus, of the electron to the two nuclei. We saw that in the Hamiltonian, but there's also electron-electron repulsion that you've got to deal with, and that can, in many cases, cancel out a lot of the benefit in potential energy. So the biggest effect for bonding is the lower kinetic energy that comes when you allow an electron to be spread out over more atoms. Okay, so that's the energy, and you can think of that as the energy you lose or you drop down on forming the new bond. Go ahead.
Part of this chapter that's confusing is just there's so many integrals with seemingly arbitrary names.
That's right.
Core integral, resonance exchange.
Yeah, core integral. You might also call that a Coulombic integral. That's your, I don't know if any of you remember back in 351 when we were doing these orbital diagrams and we had the starting orbitals here, we had our so-called non-bonding line, we had our bonding orbital down and an anti-bonding orbital up. The core integral is basically the non-bonding line. It's where you were before you formed a bond. And to a first approximation, the energy of the bonding orbital should be something like HAA minus HAB.
Is HBA the anti-bonding?
No, it turns out that, I'll show you where the antibonding orbital comes from. You could write the other integral that you're referring to is where you take the Hamiltonian applied to wave function A and then multiply it by wave function B. integrate over all space, that's called HBA. And in general, if the two atoms, in general, we're going to assume that HAB equals HBA. That should especially make sense if the two atoms are identical.
So to get the anti-bonding energy, you just add it instead of subtracting.
Right. Although I guess I spoke wrong. I should point out that HAB is a stabilizing number, so it's negative in sign. So actually, the bonding orbital should be like HAA plus HAB because it's a negative number. Okay? But don't worry about that just yet. Okay? So already we're simplifying our expression. Now let's deal with these. We've dealt with the integrals on the top, right? So we're going to replace this one here with HAA, this one here with HAB, this one here with HAB, which is equal to HBA, and this one we can also replace with HAA because HBB is the same as HAA. All right? I know it's a slog, I'm sorry, but it has an important punchline. Now at the bottom, let's discuss what these integrals are. The integral of the wave function for A times its complex conjugate over all space, we're going to call that equal to 1. Has to be, right? Has to be. The probability of finding an electron in that atomic orbital integrated over all space has to be 1. Okay, and that is going to be true for the same analogous integral for atom B. So that's the sort of self integral. The next one that we've got to deal with is what is called the overlap integral. This is where you take the wave function A and find its complex conjugate and then multiply it by wave function B, or you could do the same thing the other way. We're going to assume that these are equal. And this is, we're going to give it the letter S, and we're going to call this the overlap integral. And this has a physical meaning too. You can think of this as the extent to which these atomic orbitals, and I'm sorry about the penmanship, overlap in space. That may not be exactly what it means, but it's fine for you to think about it that way. And this number is non-zero when the orbitals are touching or when they're not orthogonal to each other. All right? Kim?
This might be premature, so you can stop me. Is that S the same for both the anti-bonding and bonding equation that we're eventually going to derive?
Yes.
It's the same number?
It's the same S.
Okay, I'll ask my other question later then.
Okay. I think so. Sometimes your text puts subscripts on the S, but I don't think I find that necessary.
Yeah, just, if it's the same number, then it kind of confuses me how we draw the conclusion about the anti-bonding orbital being more destabilizing. But we can talk about that later.
Yes, because one is going to be plus S and one's going to be minus S.
Right.
We'll talk about that in just a
Okay.
little bit. So we can actually rewrite our expression for the energy based on all of these things. It's going to be Ca squared times HAA plus 2CaCb times HAB plus CB squared times HBB. And then we're going to divide that by Ca squared times 1. We'll leave the 1 out, plus 2CaCbS plus CB squared. Okay. So, at first glance, it may look like we've made things worse because we've now got an expression for energy, that depends on coefficient A and on coefficient B, but it also depends on several other numbers that we don't know. We don't know what the core and resonance integrals are. And by the way, I should have made the substitution HAA there. That's going to make our life a lot easier. Remember, HBB and HAA are equal to each other. So we've got an expression, but we got too many unknowns. Our real question, though, is going to be, can we pretend like we don't need to know what these numbers are? Can we carry them through as variables? And can we find expressions for CA and CB that will give us the lowest possible value for energy? There's something in quantum mechanics or in computational chemistry called the variational theorem, and it applies to certain kinds of calculations, but it basically says your calculated value is always going to be higher than reality energy. And so if your energy is as low as possible, that's the best possible estimate you can make. It's probably more technical than that. I'm sure I've screwed that up. Okay, so here's the jump. Here's the bigger jump than the jumps we've been taking. How can we find minimum possible values for energy? If I wanted to find the minimum of a parabola, x squared plus 2, what would I do? I'd take the first derivative and then what? Set it equal to 0, and then I would have the value of x at which my parabola is at a minimum, right? Remember that from calculus? It's kind of a while back. So what we're going to do is the same thing with the energy. We're going to take the first derivative of energy with respect to each coefficient, set it equal to 0, and then see if we can solve that. And that will give us a value for the coefficient that is guaranteed to make energy as low as possible. Should I say that again? Maybe it'd be worth saying it again. We're going to find the value of CA that gives us a minimum in energy by taking the first derivative of energy with respect to CA. So that would look something like this. First derivative of energy with respect to CA equals 0. Now, the notes that I've posted show in detail how to do that differentiation, but this is not a calculus class, so we could do it by hand here, but it would be more about the math than it is about the chemistry. So I'm hopeful that you will allow me to show you the results of that process without taking you through it step by step, because you can see it in my notes. Is that okay? All right. Energy has a numerator and a denominator, so you end up having to apply the quotient rule, and it's all fine, but it's better not to. Go ahead, Kim.
The only part that I had a question on going through it is there was like, I think an algebra step where it somehow went from like fractions over fractions to like the dn over dca minus n over dd over dca.
Okay.
Do you know what part I'm talking about?
Yes, I'm going to actually just skip out of this notability file and go to my own lecture notes.
Yeah, going from that to
You talking about here?
yes, that, and then and then down at the bottom where where you simplified it to dn over dca minus n over d.
Oh, okay. So this part here is just the quotient rule?
Well, I understood that.
Okay,
part.
you got that.
It was the algebraic simplification.
Oh, okay.
thing, both.
So I am just, what are we doing
So I
there?
tried multiplying it the whole thing by 1 over d squared, but that didn't work. Or I'm just really don't know how
Oh, it has to do with the fact that we've set it equal to 0. I'm sorry, that was a bit of a jump. So if we say this is equal to 0, then I can multiply both sides by whatever the heck. I can multiply my expression by whatever I want as long as I do that to both sides.
Right.
So what I've done is multiplied both sides by d. That turns this d into a d squared, which cancels it out and gives you just that. And then n times d divided by d squared is simply n over d.
Gotcha.
It's, yeah.
Okay.
It's a way of,
Yeah, I mean, I was trying to multiply by 1 over d squared to cancel everything out, but
yeah. Well, and again, the only reason you can do that is because we're setting it equal to
Right.
0.
Yeah.
And we're doing that mostly out of convenience because this n over d term happens to be equal to the energy to begin with. Okay? So then I go back, and if I calculate the first derivative of the numerator with respect to CA and the first derivative of the denominator with respect to CA, then I get my answer. Is that any other questions about that, Mario?
Sorry, yeah, I couldn't understand very well because according with my math, the first term will be divided for d, but you put the d only in the second term.
Here?
Yes.
Oh, it's because he multiplied d.
So
by
up
d.
here, I'm going to multiply both sides by d.
Oh.
So this becomes d squared
Oh.
and gets canceled out.
Got it, sorry.
No, that's fine. That's fine, no problem. All right. And I'm happy to talk more about that math if you'd like to. We can set up a Zoom session for any number of you individually, and we can talk about that if that would be helpful. So the equation we get when we do all of that is 0 equals coefficient A times HAA minus energy plus CB times HAB minus energy times S. All right, and I realize that's a jump. You may look at that and say, well, one easy solution for this is for coefficient A and coefficient B to equal 0. Fine, but that's a boring solution. We don't want to know that the coefficients are equal to 0. They need to have real or non-zero values if bonding works, which we all know it does because we're alive. So if we do the same thing for coefficient B and set it equal to 0, we get the following equation: CA times HAB minus ES plus CB times and I guess we can just say HAA minus E. Okay. 2 equations, 2 unknowns. At this point, we can solve it any way we like. By algebra. It just so happens that a convenient way to do that, at least for the people that write these texts, is to write it in matrix form. So I'm going to just you might be uncomfortable with that, but even Mormon does it in the Book of Mormon, which being interpreted is, and then proceeds to say a word that doesn't actually help very much.
Josh, when you're saying 2 equations, 2 unknowns, you're just saying we don't know CA and CB. We also don't know these other things, but we're going to pretend that we
We're gonna keep them
constant.
as though they were constants.
Okay.
Yep. Yeah, it is interesting what pretending like you know things can do for being able to draw out of a system as much as you can know with what you know. I guess there's a sort of fake it till you make it, honestly, in this way. So if we make the matrix look like this, and then we multiply it by the following single column matrix or vector, and we'll set that equal to this single column matrix or vector. That's the same thing as what we wrote above. And the way you multiply matrices, and again, remember, it was like 1997 with my last linear algebra class, so I only barely remember this. This term times that plus this term times that equals 0. This term times that one plus this term times that one equals 0. Same equation, it's just a different way of noting it. Now, okay, I guess questions so far? We've already said that a non-interesting solution to these equations is just to let both coefficients equal 0. And there's a rule from matrix math called Cramer's rule, which I don't really remember what it is, but as applied to this situation, it basically says the only way that this situation has unique non-zero solutions is if the determinant of that matrix is equal to 0. Now, I tried to reteach myself Cramer's rule and figure out where it came from, but unfortunately for me, the Wikipedia article on Cramer's rule and matrix math was unintelligible, to me anyway. And so you are going to have to, I suppose, accept this on faith. Our two equations up here only have non-zero values for CA and CB if that determinant equals 0. Go ahead.
Yeah, more commonly when using Cramer's rules to solve systems, you take the answer matrix and substitute it in for one of the columns.
Okay.
So with 0 being our answer, if we substitute that for any column, it will give a determinant of 0 for this.
Okay.
And in order to keep the coefficient from being 0, the denominator has to be 0 as well.
Okay. That sounds great. Dakota understands it. That's fantastic. I will need to talk to you again so you can explain it to me. But thank you. That's really good. So determinants, if you recall, involve for 2x2 matrices, and that's all the determinants we're going to do, so don't worry. If you've got A, B, C, and D, it's A times D minus B times C. So we can rearrange this into HAA minus E squared plus, quantity squared minus HAB subtracted ES quantity squared equals 0. And all of a sudden, the world is looking a little bit brighter because we don't even have to use the quadratic formula here. We can simply take this equation, subtract or add. This is not actually saving me any time. I probably should have just written it out again. I thought I would be cute, but alas. We can move the minus HAB minus ES quantity squared to the other side. Then we simply take the square roots, so we can say HAA minus energy equals, we have to remember that when you take the square root of something, you've got both positive and negative values. HAB did I screw something up? Minus ES. Okay?
One question I had here, Josh, is I didn't understand why it wasn't plus and minus on both sides, since we're taking the square root on both sides. Shouldn't it be plus or minus HAA minus E as well?
Yes, but what will matter here is the relative relationship? Are they both plus, or is one plus and one minus? Yeah?
Yeah, we don't need a second plus or minus there because the one on the right would cancel it out. Like plus plus is the same as minus minus in this case.
Okay.
Just divide by negative, or multiply by negative 1 and you get the
Right. That's a great question, Kim. And it sounds like there is an answer. Thank you, Dakota. I'm going to summarize it as because maths. Sorry. So what we're going to do is we're going to try to get E on the one side of the equation and everything else on the other side of the equation. And I won't do that algebra, but what you come up with is E equals HAA plus or minus HAB divided by 1 plus or minus S. You got to keep the pluses and minuses, you got to follow those through in the algebra to make sure they're consistent on top versus bottom. Okay, so magically out of this process, we have found two minimum energy values that satisfy the Schrodinger equation. We don't yet know what the wave function is, but we know what the energies of those two wave functions are, and we've got them here. So let's remind ourselves that HAA is a negative number representing the attraction of a nucleus to an electron plus the electron's kinetic energy. HAA is the starting line, which isn't.
Oh, negative
If the 0 point is infinite separation of the electron from the nucleus, then HAA should be negative. But then HAB is also negative, stabilizing to be between the two nuclei. S, we're going to say it's a overlap integral, so the overlap can't be zero, or can't be negative. It has to be either 0, it has to be somewhere between 0 and 1. So maybe we'll indicate that here. Okay. So let's look at the two cases, and we can decide which one is bonding and which one is anti-bonding. HAA plus HAB divided by 1 plus S. That's one of our values. And then HAA minus HAB divided by 1 minus S. And let's imagine that this dotted line is sort of the HAA. Okay. Which one of these two is a bonding versus an anti-bonding energy? Is this one lower or higher than HAA? Lower in energy because HAB is negative, right? And for right now, let's pretend that S is equal to 0. Okay, if S is equal to 0, then we should go down by an amount that is equal to HAB. So this would be HAA plus HAB. Good. That would be our bonding orbital. And then subtracting negative number HAB from HAA should take us up by the same amount, HAB, to give us the anti-bonding orbital, which has an energy HAA minus HAB. That's if S equals 0. Go ahead.
So S here essentially determines the difference in how much the bonding shifts versus the anti-bonding.
Bingo. Bingo, Austin. Say that again. I need to hear that again.
The S determines how much the bonding shifts the energy versus how much the anti-bonding shifts.
Exactly. So the S, which represents the overlap between the two atomic orbitals, determines how much more the antibonding orbital is destabilized versus the bonding orbital is stabilized. Let's see how that might work. Okay. So let's pretend that S equals 0.5 because I can do maths that involve dividing by 2. All right, if S equals 0.5, we have HAA plus HAB divided by 1.5, right? So now instead of going down by a full increment of HAB, we're going down by less than that. Okay? So the effect of having a non-zero S will be to attenuate or decrease this stabilization energy, right? On the other hand, what does that do up here? HAA minus HAB. If S was 0, we'd be destabilized by HAB. What if S is 0.5? Now we're dividing this number by a number less than 1. So now we have the energy of the new orbital should be this one times 2. Okay? So that would tend to make this orbital much higher in energy. If you wanted to, you could actually look for what an expression for the number HAA minus E, which would tell you how much your energy changes. And you could do that math and it would convince you that S determines how much less the bonding orbital is stabilized by the antibonding orbital. Okay? So, and that's a general rule that we're going to deal with. And this is a nuance that we did not talk about in sophomore organic, that this number, we'll call it delta E for the bonding orbital, its magnitude is always going to be less than delta E for the bonding orbital. So because signs will be different, we're going to say that the anti-bonding orbital is always destabilized by more than the bonding orbital is stabilized. Okay? It's not just a reflection. Now, why should we care about that? What does that have to do with any chemistry? Well, it actually has to do a lot. It is the origin of something called closed shell repulsion, which basically says if you have two orbitals and they're both filled and you bring them together, you're going to get a net destabilizing effect. It's not just neutral, it's actually bad, right? So this is the origin of what we call closed shell repulsion, which is behind, say, the van der Waals radius of atoms, how they bump into each other like spheres and don't occupy the same space. It's also behind steric hindrance, right? Why is T-butyl so big? Well, it has electrons, and if those electrons lots of electrons overlap with filled orbitals in some other part of a molecule, there's going to be repulsion. Not only electron-electron repulsion, but also net destabilization if the orbitals get close enough to overlap. Okay. All right. So let's see. Now that we have our values for energy, we can substitute those values for energy back into this equation. No, not that one. We can substitute it back into these equations. Plug those energy values for the bonding orbital and the anti-bonding orbital one by one into these spots. And if we do the math, we can solve for what Ca and CB should be when the energy is at the bonding level. And it just so happens that at the bonding level, we determined that Ca equals Cb. The coefficients are the same. Well, that's sort of a trivial result, which we probably could have predicted from the beginning. The two atoms are the same. They have equal energy. So when they form a bonding orbital, it ought to be evenly between the two atoms. And at E antibonding, we come up with the conclusion that the coefficients have opposite sign in the antibonding orbital. So for our bonding orbital, we net.
Real fast.
Yeah.
So when you solve for those things, are you just doing like matrix multiplication, a 2 by 2 matrix multiplied by 1 by 2?
Oh no, I'm not that smart. I just do the substitution, two equations, two unknowns, isolate a variable, and then substitute it into the other equation, and then solve.
Gotcha. So you just treat it as 2 equations, 2 unknowns.
Yeah.
And you just put in energy bonding, 2 equations, 2
Yep.
unknowns. Energy antibonding, 2
Yep.
equations, 2 unknowns. Okay.
Now notice that this hasn't given us exact numerical values for the coefficients. It's just told us their relative values and signs. We know that in the bonding orbital, say this is two hydrogens, hydrogen A and hydrogen B, our bonding orbital should look something like that, where it's equal magnitude on both atoms. Okay? Whereas our antibonding orbital, we know is going to have a node in between the two of them, and the magnitude is going to be the same but opposite in sign. Okay? Which is the origin of all that stuff I told you about antibonding orbitals coming from destructive interference between the two wave functions. Okay? Now, we don't yet know what the values of Ca and Cb are. It turns out we can get that now with our new definitions for wave functions. So we'll call this one I can't decide what to call them. I keep going back and forth. We'll call it bonding. That's going to equal Ca phi A plus Cb phi B. Well, good, because that's what we thought it was to begin with. Go ahead.
So basically then the bonding energy is a point on the surface for the equation where the energy has a minimum. And
Yes.
the bonding is where there's a maximum.
Yes. Yeah. The antibonding and the bonding energies are places where the first derivative with respect to the coefficients is 0, so it's a minimum in energy or a maximum in energy. Yeah.
We caught both of them because they're both points where the derivative is 0.
That's right. We caught both of them because they're both points where the derivative is 0.
Can there be any saddles with this equation?
Can there be saddles with this equation? I don't know. Michael, do you know anything about saddles on a potential energy surface?
There is always saddles, but I'm
Okay.
not sure with hydrogens.
So I don't know a lot about it. I don't think in this case, but yes, on a potential energy surface where it's multi-dimensional and has lots of degrees of freedom, there can be saddles, and they often represent transition states. Yeah. Great question. What is a potential energy surface? I think we're just imagining, and we'll talk about this more later, but if you take, say, those two hydrogen atoms and you decide there's some way to monitor all of the possible ways that they can move relative to each other. So in this case, the radius r might be the simplest. The potential energy surface for hydrogen would be plotting energy versus all the possible values for r. And it turns out for hydrogen, at long distances it's about 0, and then as they come closer you get to a minimum in energy, and then as they get beyond that you start to get repulsion between the two nuclei, and then the energy goes up a lot. For molecules that are bigger than that, they have lots of different ways in which they can move, and so the potential energy surface is not a simple line, nor is it a simple three-dimensional surface. But you can imagine it as like a table or a plane, and there are mountains and there are valleys, and the valleys are low energy, the mountains are high energy. And we will generally find stable molecules will have to be in those valleys. And this is one of the ways we can determine where those valleys are. So at this point, I guess it looks like we're out of time. I want you to look in the notes that I've given you. Your text explains this too. Basically, if you make the assumption that if you multiply the bonding orbital by its complex conjugate and set that equal to 1, you can figure out what the coefficients should be, what their actual numerical values are. And they depend, I mean, this is interesting, they depend on S, which is kind of cool. All right. With that, I think we will pause. We still have tons to do in Chapter 14. We're going to take it slow and figure stuff out. Next time, we're going to talk about how the math changes when the two orbitals are not equal in energy, which is kind of fun, and except the algebra is bad, so we will ignore it. All right. Have a good weekend. Have a fantastic Labor Day.